Dear colleagues, dear students, and dear fellow participants of International Astronomical Congress, welcome to this International Astronomical Congress of 2020. Right now I want to present my paper and my presentation on advanced nuclear propulsion methods for deep space missions. I'm Dr. Ruben. I'm an aerospace and a nuclear engineer, and my area of expertise is nuclear space propulsion. I have been working on it for 25 plus years. As you know, since the advent of the first start of the space age, with the launch of the Sputnik in 1957, civilizations, governments, mankind, space agencies, companies, organizations, universities, academia, all have been working toward making space travel a possibility. Obviously, as far as manned missions are concerned, the furthest distance that we could reach was the moon. But as far as unmanned missions have been concerned, a variety of missions have been launched. We had a probe which has gone to Mercury, Venus, Mars, Jupiter, even Uranus, Neptune, and Pluto, with various missions. So since 1970s, we had unmanned missions to almost every corner of our solar system. As you're aware, Voyager 2 surpassed our solar system a couple of years back by passing through the heliopause. But all of these missions are very, very long-term missions. And if you want to go to outer reaches of our solar system or to beyond interstellar space, we need to have much faster ways of getting there. And that's why nuclear propulsion is one of the most interesting propulsion methods that's available to mankind. Obviously, a lot of work has been going on in the past past decades. Project Adelius, Project Icarus, Project Orion, all of them are basically various nuclear propulsion designs that have been done in a futuristic manner by various organizations, including the British Interplanetary Society. NASA has been working on NERVA in the 70s. Russians had their own version of nuclear propulsion. And while this work was halted because of some United Nations resolutions due to an atmospheric explosion of one of the Russian nuclear satellites many decades back, still nuclear propulsion seems to be the most feasible way. Why is that? To understand that, we have to understand important parameters for propulsion. One of the most important parameters for propulsion for reaching longer distances, first of all, is specific impulse. Specific impulse, as you can see from the equation on the left of this slide, is exhaust velocity VE divided by G, which is our gravitational constant. And if you look at the equation on the right, which is highlighted in white, exhaust velocity depends on a variety of factors, but the most important factor is the parameter you see on the middle, where it says T and a subscript of C. TC means the combustion temperature. So basically, if you have a rocket which works on a principle of combustion, you need to obviously have high TC as possible, because high TC or high temperatures would mean higher exhaust velocities. Higher exhaust velocities would mean higher specific impulse. So that's why nuclear propulsion methods are very important for deep space missions. Because first of all, compared to standard chemical propulsion methods, with nuclear propulsion you would actually reach temperatures of a couple of thousand Kelvin, which would obviously mean higher exhaust velocity and higher specific impulse. If you were to, for example, take fusion instead of fission, then you would reach 1,000,000 degrees Kelvin theoretically. But while that would give you very high speeds, you would also have the problem of containing this temperature. So if you look at different types of nuclear propulsion, obviously the one on the left, the nuclear thermal propulsion, is the most common type of propulsion method that can be used. Basically, you have a fission reactor which breaks down nuclear fuel, and during this breakdown process you have energy which is released, and this energy can be imparted to, for example, propellant like hydrogen, diatomic hydrogen, which will be then discharged from the rear of the spacecraft. And this discharge, or the exhaust velocity of the gases, would create an opposite reaction where the spacecraft would have a forward momentum because of the discharge, high speed discharge of these particles. Obvious efficient propulsion would give you a lot of flexibility. For example, if you want to have a mission to Mars, you would not have to wait the window of opportunity. You could theoretically just launch it at any time, and if a 600-day mission could easily be accomplished in 200 days, 1/3 of the time, with the proper mission planning. The one you see in the middle is the fusion propulsion. Fusion propulsion is a very advanced form of propulsion. While a lot of sample engines exist even from 1970s on nuclear thermal propulsion, we don't really have fully workable engine of fusion propulsion because of the very, very high temperatures involved in having such a reaction. In one of the slides I showed that Project Adelius. This was a work on how to create a fusion propulsion system, maybe by creating small fusion explosions to propel the spacecraft forward. But like I said, there are a lot of technical challenges. The one you see on the right, gaseous core propulsion, is actually also a fission propulsion. But the difference between this and regular fission reaction is that you don't use solid nuclear fuels, you don't use water as coolant, you actually use gaseous form of a nuclear fuel called uranium hexafluoride, UF6. Because you are using a gaseous fuel and gaseous core, technically you are reaching temperatures about 10,000 K, which gives you obviously a large exhaust velocity. Imagine the gaseous core, you have gaseous reaction of uranium hexafluoride, you impart this 10,000 K to a diatomic hydrogen, you expel it from the rear of the spacecraft, and you have a very fast spacecraft that can move and cover large distances in a short amount of time. So of course the distances are very huge. Here I've given you some sample work. You could read my paper more to see more detail about this, but to go to, for example, Alpha Centauri, which is the one on the right, you have to travel about 4.3 light years. So even taking account the relativistic effects going at semi-relativistic speeds, because nuclear propulsion will only give you a fraction of light speed, still it would take you about 11 years or so to reach. If you look at Barnard star, which is another possibility you can reach beyond our solar system, it's 6 light years away. Normally it would take 6 years to reach if you have going at the speed of light. With nuclear propulsion you will be able to reach there roughly on 16 years, 15.4 or 5, etc. This would be by shipboard time 14 plus years because of the semi-relativistic effects. So technically, if you had a properly mission planning, you could reach Barnard star in 15 years using nuclear propulsion. So that's why it's something we can still use with 21st century technology. That's why there's a lot of interest going on in nuclear propulsion. I've been working with nuclear propulsion techniques for the last 25 years, and I do believe that it's the future of mankind and space travel. Please feel free to go to my website, www.drgwen.com, to see my other research. You can contact me for interest in nuclear propulsion at drgwen@live.com. Thank you very much, and enjoy the rest of the International Astronomical Congress.